Hello everyone, welcome to the 10th lecture of the course Statistical Thermodynamics. The topic of this lecture is a review of classical thermodynamics, specifically the second law of thermodynamics. In the previous lecture, we have seen that every object in nature has a property called entropy, which is not as obvious of a property like mass or volume, but nevertheless, it is a property whose change is well defined and calculable. However, we have not learned what this property or even its change tells us about the behavior of a system. That is the content of the present lecture. One place to start is the expression for the change in entropy, which is ds is equal to del Q reversible by T. This suggests that if a system absorbs heat, its entropy increases. So an object, when heated, has more entropy than when it was cold. But this is true of the internal energy of the object also. So how is entropy different? The other thing we notice from this equation is that the same heat causes a greater increase in entropy of an object if it were absorbed at a lower temperature. This again does not help us much in answering our question about what entropy change tells us about the behavior of a system. To answer this question, let us consider one of the most familiar and universal processes that happen in nature and calculate the change in entropy for that process. I am talking about the heat flowing from a hot object to a cold object. Consider specifically two reservoirs or very large heat capacity objects whose temperatures do not change when a finite amount of heat is absorbed or removed. Let us say one of these reservoirs, the hot reservoir, has temperature Th, while the other reservoir, the cold reservoir, has a temperature Tc. Let us calculate the change in entropy of both these reservoirs when a Q quantity of heat flows from the hot reservoir to the cold reservoir. Keep in mind the sign convention that heat absorbed by a system is positive and the heat lost is negative. Further, the temperature of the reservoirs remain constant during the heat transferred, and the heat released and absorbed are reversible. The change in entropy of the hot reservoir is delta S hot is equal to minus Q by T hot. And the change in entropy of the cold reservoir is delta S cold is equal to heat absorbed divided by the temperature at which the heat was absorbed. If we add these two up, minus Q by Th plus Q by Tc, the net change in entropy in the process is positive because Q by Tc has a greater magnitude than Q by Th. If we consider the hypothetical process of heat transferring from the cold reservoir to the hot reservoir, like this and calculate the change in entropy for this process, we find that minus Q by Tc plus Q by Th, the net change in entropy for this hypothetical process is less than 0. Clearly, the net change in entropy is positive for a process which is allowed, while it is negative for a process which is not allowed. So delta S greater than 0 for this allowed process and delta S less than 0 for this process which is not allowed. Although heat transfer is a very specific type of spontaneously occurring process in nature, it turns out on examining a variety of processes that this statement, delta S positive, is true not just for heat transfer processes, but for any spontaneous process in nature. This is essentially the second law of thermodynamics. The second law of thermodynamics can be stated in several ways, and each way implies the other. The statement I find most instructive is, for any process that happens in nature, the condition delta S universe greater than or equal to 0 is satisfied. This implies that only those processes can happen in a system where the sum of the change in entropy of the system and its surroundings is either 0 or positive. This is a very powerful result in understanding and predicting the transformations of matter. Only those transformations will take place for which the entropy of the universe either remains constant or increases. The entropy of the universe never ever decreases. Note that the word universe here has simultaneously two meanings. The first meaning of universe is the system plus its surroundings. The second meaning is the whole universe. Clearly, if the entropy of the system and surroundings increase, the entropy of the whole universe increases because the system and surroundings are part of the universe. This might lead to a question in your mind about whether this increase in entropy of the whole universe is indefinite or there is some end to it. The answer to this is that there is an end when the entropy reaches its maximum value, but you will get a better appreciation for this after we discuss the microscopic picture of entropy. Let us now verify the second law of thermodynamics for a few situations. The first situation is a heat transfer process from a hot body to a cold body, but the difference from what we have considered a few minutes back is that now the bodies have a finite heat capacity. So consider two equal masses of the same material at temperatures Tc and Th brought in thermal contact. Here, the two objects have the same heat capacity. Th is greater than T cold. And the question is, what is the change in entropy during this process? So what is delta S? And is this change in entropy greater than 0? Let us calculate and find out. When these two equal masses of temperature Tc and Th are brought in thermal contact, the final temperature of both these masses is T is equal to Tc plus Th divided by 2. Now this process of heat transfer is not a reversible process. So to calculate the change in entropy of each of these objects, we have to consider or imagine equivalent reversible processes. That, for heating the cold object, would amount to putting this object on a thermostat which has initially the same temperature as Tc, and then increasing the temperature very slightly to Tc plus delta T and allowing it to equilibrate, and then increasing the temperature further and keeping on repeating this process all the way till the temperature becomes the final temperature T. A similar reversible process has to be imagined while decreasing the temperature of the hot object from Th to T. So using this reversible paths, the change in entropy of the cold object delta S cold is equal to mc integral T cold to T final dt by T, where the Tf here is the final temperature of the two objects. This is equal to, on evaluating the integral, mc ln Tf by Tc. Similarly, the change in entropy of the hot object is equal to mc integral T hot to T final dt by T is equal to mc ln Tf by Th. Note that this quantity is negative because T final is less than Th. The net change in entropy of this process is the sum of the change in entropy of the cold object and the hot object. So delta S process is the sum of these two, that is mc ln Tf by Tc multiplied by Tf by Th. That is equal to mc ln Tf squared divided by Tc Th. Now the question is this entropy of the process greater than 0, or in other words, is this term in the ln greater than 1? In other words, is Tf squared greater than Tc Th, and writing Tf in terms of Tc and Th is Tc plus Th squared greater than 4 times Tc Th. Let us open up the square. So this becomes Tc squared plus Th squared plus 2 times Tc Th, and we are asking if this is greater than 4 Tc Th. Now let us take this term on the right hand side to the left. So we get Tc squared plus Th squared minus 2 times Tc Th, and we want to know whether this is greater than 0, and we see that this is a perfect square. So this is Tc minus Th whole squared, and this is indeed greater than 0. So yes, here, and this implies that this term here is greater than 0, and therefore the net change in entropy of this process is greater than 0. Let us now consider another situation where we will calculate the change in entropy. This second situation we will consider is a cup of hot tea initially at temperature Th left untouched so that it eventually attains the temperature of the room. The question is, what is the net change in entropy of the universe during this process, and is that greater than 0? Let us say the initial temperature of the tea is Th and the room temperature is T-RT. By constructing a reversible process for the tea cooling down, the delta S of the cup of tea is equal to mc integral Th to T room temperature dt by T is equal to mc ln T room temperature divided by T of hot. You see that this quantity is negative, so the tea cools and its entropy decreases. Now what about the room? The change in entropy of the room needs to be calculated, and for this you have to realize that the room is a reservoir with a very large heat capacity, and its temperature does not increase when it absorbs heat from the cup of tea. All the heat that it absorbs from the cup of tea is at room temperature reversibly, because there is no change in the temperature of the room, and the change in entropy is mc Th minus T of room temperature divided by the temperature of the room. This is clearly a positive quantity. The net change in entropy of this process, or the change in entropy of the universe, is the sum of this negative quantity and this positive quantity, and that delta S of the process or of the universe is equal to delta S T plus delta S room should be greater than 0. Let us check this by taking some reasonable temperatures. So let us say the initial temperature of the hot tea is 80 degrees Celsius and of the room is 30 degrees Celsius. So the change in entropy of the universe for this process is mc ln of room temperature. So it is 30 plus 273, and it's very important to consider absolute temperatures in this ratio of temperatures. 80 plus 273. Without using absolute temperatures, you will get a completely incorrect answer. So be careful about that. And plus TH by TRT, so that is 80 minus 30. This is just a difference of temperatures divided by room temperature, which is 273 plus 30. And if you evaluate these numbers, this becomes MC minus of 0.153 plus 0.165, which is equal to 0.012 MC, which is positive. This is how much the entropy of the universe increases by as a cup of tea sitting in a room cools down to attain the room temperature. We will now consider the third and final situation for now. This is a really interesting situation. So consider a chamber like this, and the chamber has a partition right in the middle here. And let us say that there is an ideal gas in one side of the chamber like this. This chamber is thermally insulated. So no heat can flow in or out of this system. You see here the initial state of the system. Let us now remove this partition. And you know intuitively what will happen. The gas will expand to fill up the entire chamber. The question is, what is the change in entropy of the universe during this process of the gas expanding within this chamber? Since the chamber is thermally insulated, there is no heat flowing in or out of the system. So Q is 0. The gas expands against a vacuum. This was initially evacuated, then there was nothing in there. So the work done by the gas is 0. So from the first law of thermodynamics, the change in internal energy of the gas is also 0. So here is a really interesting process. There is no heat absorbed, no work done, no change in internal energy. Yet, this process is spontaneously happening. So you would think that there is a change in entropy of this process. And you would be right in thinking so. So can you calculate the change in entropy of this process? Pause the video and try. Because if you're able to do this, you have followed everything so far about calculating entropy. This is an irreversible process, and as we have discussed earlier, to calculate the change in entropy, you have to consider an equivalent reversible process which has the same initial and final states. A process satisfying this condition is an isothermal reversible expansion, and we can use that to calculate the change in entropy. For an isothermal reversible expansion of an ideal gas, we have already calculated the change in entropy in the previous lecture. Please refer to that if you don't recall that discussion. The change in entropy, delta S, of this system is nr ln V2 by V1, where V2 is the final volume and V1 is the initial volume. Since this system is isolated from the surroundings, there is no change in entropy of the surroundings. So the change in entropy of the system is the change in entropy of the universe. This is true for any isolated system. And in this case, we can see that this change in entropy of the system is greater than 0 because the final volume V2 is greater than V1. As you can imagine, you could consider any other reversible path to go from this initial state to the final state, and the change in entropy calculated would always turn out to be the same. Let me emphasize again that in this process, there is no heat transfer, and yet there is a change in entropy. So, although the formula of change in entropy is reversible heat transferred divided by T, a transfer of heat is not necessary in every process, but yet there is a change in entropy, and to calculate that change in entropy, you have to consider an equivalent reversible process in which there is a heat transfer. There are a few points to note. The change in entropy of the universe during a reversible process is zero. This implies that a reversible process can be run backwards and the system and the surroundings can be restored to exactly what they were before the process was done, and nobody would know. The second point is that for any real natural process, the entropy of the universe always goes up, and this is related to dissipation of energy or work getting lost dissipatively as heat during the process. Importantly, to calculate the change in entropy of such an irreversible process, we need to use a reversible process which has the same initial and final states as the irreversible process. This reversible process is not really occurring. It is only a device to calculate the change in entropy of the actual process. Let us now consider a few interesting big picture ideas in relation to the second law of thermodynamics. The first point to realize is that every time you see an irreversible transformation in nature, you should know and think through the idea that entropy of the universe increases in the process. And interestingly, every transformation has a flow of heat associated with it, which is in the definition of entropy, although this heat flow is often hypothetical. The second point is beautifully said by Ludwig Boltzmann, and I quote, "The general struggle for existence of animate beings is not a struggle for raw materials. These, for organisms, are air, water, and soil, all abundantly available, nor for energy, which exists in plenty in any body in the form of heat, but a struggle for entropy, which becomes available through the transition of energy from the hot sun to the cold earth." This is essentially suggesting the intimate connection between entropy generation and a very special type of transformation, namely the process of life. The third point is that entropy is sometimes called the arrow of time. This essentially means that if two snapshots of an isolated system were presented to you with two different states, and one of them has a greater entropy than the other, then you could say that the state with the smaller entropy existed at a time earlier than the one with greater entropy. So entropy of an isolated system can be a marker of time. The final point to note is that after this and the previous lecture, we now understood that every object has an entropy. We know how to calculate its changes, and we know what it tells us about the behavior of a system. We, however, still don't know what exactly this property means. We might have heard before that it is a measure of disorder and such things. But so far in our systematic study, there is absolutely no indication of any of that. There might be a small hint to that idea in the fact that entropy change is delta Q reversible by T, so the same quantity of heat absorbed reversibly at two different temperatures can cause a different increase in entropy. But it is really not clear. To understand what entropy really means, we need to understand it microscopically. In other words, as mentioned in the first lecture of this course, we need to understand the statistical approach to thermodynamics. We will soon appreciate how the statistical approach gives us a clear and intuitive, at the same time, a beautiful picture of what entropy exactly is. We have almost completed our review of classical thermodynamics. Classical thermodynamics culminates with the second law of thermodynamics. There is really nothing more to it. It is now about application to specific systems. In that context, before moving on to statistical thermodynamics, I would like to cover two more ideas which are important to apply thermodynamics to chemical systems. These are the concepts of Helmholtz and Gibbs free energies and the Maxwell relations. See you for the next lecture.